Well, let me get you started. And I waited too long yet again. But nonetheless, let's start because I want to spend the entire time really diving into the mathematics of this chapter. And as we begin to see last time, there was some interesting and maybe even some challenging mathematics. And we did the ring. In fact, that's kind of where I want to begin here. Let's quickly summarize where we left off, what we've done so far in this chapter, which I might say is not too much, but I think I did get across this, that chapter 30 is about looking at these sources of the magnetic field. And as I asked last time, and maybe I'll ask again, where does all magnetism come from? Where does the magnetic field? What creates the magnetic field? Yeah, moving charges, any kind of current. And so I pointed out that there's going to be two main approaches that we're going to take. One is very similar to Coulomb's law. That's the one we got started on. The Biot-Savart says this, that if we can figure out, or here was their logic, if we can figure out the magnetic field created by a small little chunk of current, realizing, of course, you can never have a small little chunk of current by itself because it has to flow from someplace and have to go someplace, all right? But if you could think of a little chunk of current all by itself, how much magnetic field would you get from that? And so that's where I want to spend the first time. The second hour, let's jump over in here to Ampere's law. As I mentioned before, Ampere's law is kind of looking at all of the current or all of the sources as one big chunk, just like Gauss did. So we have Gauss's law. And so when we did electric fields, saw these two in two separate chapters. This one, your author puts both of these in one chapter and some other things, which is where I want to pause here at the beginning. Those other things, I'm not going to attempt to really cover in great detail before the test. I mean, maybe we'll even get them before the test, but you certainly won't be tested on them. Here's what I mean by that. Make a note of this. I'm going to turn to sections. Let's see, chapter 30 we are at. But in chapter 30, your author starts off, as I said, with Biot-Savart and says, let's look at the magnetic field created from that. And so that's what I want to spend a long time today working with. After that, he says, let's look at the current collectively. Let's take Ampere's approach, okay? And then I want to spend a lot of time on that. And that makes a good chapter by itself. After that, he gets into section 5. Where it is Gauss's law of magnetism. And then he gets into section 6. Both of those are neat topics, and we need them for next chapter. So I thought what I would do is emphasize that for this chapter and for this test, this is what I'm going to focus on. Section 5 and section 6, you can just make a note to yourself. We will do, but it won't be on this test. It'll be on next test. It will be what I will call the start of chapter 31. So I'm going to treat section 5 and section 6 really as the start of chapter 31, okay? And I think it fits a little bit better there. It's not quite what your author does, and I wanted to point that out as I get started. So I'll say it again. Here's the goal for today, to get these two main approaches. That's our chapter 30, and that's where we'll say end. That's what your test is going to be. Since we pushed the test back a little bit, we'll even go ahead and do probably section 5 and section 6 before the exam begins, as we are thinking of it starting chapter 31. But I want to think of it as starting 31 is my point here. All right, so again, back to our summary here. Here's where we came off. If it was Gauss's law, we said a little bit of an electric field is created from a little bit of charge. Its value depended on a couple of constants, how far away you are, and a straight radial direction. The magnetic field, though, as we saw, was a little more complicated. The magnetic field, and so a little bit of a magnetic field, as this picture was trying to show here, we said, let's look at the magnetic field at the point P, which is coming from this little chunk of wire, ds. What would it depend on? And so it depended on a couple of factors from nature, where this 4 pi times 10 to the minus 7 was our constant, like the permittivity of free space. This becomes the permeability of free space, so the same idea there. It also depends on how far away we are, so again it has the 1 over r square value. I think you saw that in the lab we did last week. We measured the magnetic field as we got further and further. We were trying to show that it was a 1 over r squared value. Most of you got a pretty good value of 2 there. Its number, or its strength, its source, if you will, comes from the current. That's probably the most important piece of there, if you can say one is more important than the other. But again, like we did last time, this is the source, this is the distance, this is the constant, and then there would be a direction. And the direction is probably the one that gives students the most headache, although, interesting enough, it actually comes out to be easy to do because of this cross product. As you'll see, the directions actually often fall into place real simple compared to the electric field. And so if we apply this little idea to this point P, as we did last time, we could look at the point P and maybe we would do direction first. And so the ds is the direction of the little chunk of current. The r hat is the direction from the chunk of current to the point where you want to know the magnetic field. The hat on top means it has a length of 1, and so the idea of this cross product is it doesn't contribute any numerical value. In other words, the magnitude of the magnetic field is contributed by these numerical values, but the direction is then determined by this cross product. So let's do the cross product. Let's get direction. And so looking at the point P up here, I would say this little chunk of current is a ds, and so as I go ds and I cross it towards r hat, now there's r hat. R hat is a vector that is 1 unit long, and it points from the source that is creating the magnetic field to the point where you want to know the direction of the magnetic field. So again, taking my right hand for vector cross products, and I want to emphasize that today. We've done right hand for vector cross products. We saw a lot of cross products, but they've all been the same basic rule. I say that because what I'm about to give you today is 2 new right hand rules that are not related to vector cross products, and you may confuse the right hand rule for vector cross products with the right hand rule that I'm about to give you. But so far we've been doing the right hand, and we've shortened it by calling it the right hand rule. But I think today I need to emphasize it's the right hand rule for vector cross products. So taking my right hand and finding the right hand rule for vector cross products, I'd go ds cross r and I'd get out of the board. And so sure enough, at that point P, there's a green dot pointing out. If I were to look at another point, which your author says let's look at P prime, and then it's over to here, then when I do the right hand rule, it's ds cross r hat. R hat is below it, I'd get into the board. So your author puts a little green X. And in fact, you can see then that any point in this kind of area would be into the board or into the screen. And any magnetic field up in this area would be out. And so there's our little cross product. And if we wanted to then know the total magnetic field, we would just have to add it all up. We would have to integrate all the current that is flowing in the vicinity, which in this case means we would have to add up along the length of this wire. In your math class, you would call this a line integral. You would add up here to 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 here. But here's what I was saying earlier. What's really kind of nice about the cross product in the Biot-Savart law right here is if I wanted to know then what is the total magnetic field at that point P, then I'd have to take this chunk plus this chunk plus this chunk plus this chunk. But let's look at another chunk. Let's look at, say, a chunk right here. ds would be this way, r hat would be this way. Take a cross product, what direction do you get? Out of the board. How about the chunk before I got there? Here, which way would it make the field there? Out of the board. How about here? Out of the board. So one thing nice about this is the magnetic field is always going to be out. And so it's nice to add up fields that are always in the same direction. That will soon change. We'll get some harder ones today here, but we did that one time. And in fact, as a quick review, let's go back to this ring. Remember we did the ring at the center? Let's do the ring at the center here again. And so if I took this ring here and said, okay, the current is flowing around this ring, and for the sake of discussion, well, actually to be consistent, which way did I think last time I had the current going this way? Or was it this way? Ooh. Anybody remember? Well, maybe we better talk about both. Because that's one thing I didn't get a chance last time and I wanted to emphasize this time. But for starters then, let's do this. Let's say that as I hold this ring, right here where this piece of tape is, let's just say the current is going towards you. So I'll hold the current up, I'll hold it so that the tape is up at the top. I'll say the current is going towards you, because what I'd like to find is the magnetic field right here at the center. All right? So maybe I'll start with the direction. What direction would the magnetic field be at the center from the current that is at the top going towards you? Well, let's see. The ds right here is towards you. The r hat vector is going to be straight down. So ds cross r hat looks like it gives me over here to the computer. Okay, so in the center of this ring, there'd be a little magnetic field pointing in that direction towards the computer from that little current. How about somewhere else? Maybe this front edge, which is closest towards you. Which way is the current? Okay, it would be down. Which way is the dr? Towards here, right? And so ds is down, closed towards me, gives me towards the computer again. And we can continue this as we did last time, but everywhere around we're going to get towards the computer. So if we call towards the computer the x direction, then what I'm going to get is the magnetic field in the x direction. Okay? And that's going to be the only magnetic field. There would be no y, there would be no z. And so that tells me that the magnetic field at the center is along the axis of symmetry. And as I go to add it up, I would say, well, what quantities, if any, are a constant here?
The direction?
Yeah, this, and actually maybe I don't need that cross product anymore, because that is what gave me, well, I better do it a little more formal. All right. Let's take the cross product. This would be the ds. This would be the magnitude of the r hat. This would be the sine of the angle between them. Okay? And so all of that would be its magnitude. Its direction I'm not even going to put up here, because that's what I meant here, that I've already figured out the direction. And what's really nice about this one, and why we did it first and then we ran out of time, was as you look at this, aren't all of these a constant around this ring? And that's why I picked the ring first, because the current in the ring is of the same value. The distance that the center is from the source is always the same distance. And so I can pull out the mu, I can pull out the I can pull out the 4 pi, I can pull out the r squared. And so now my integral becomes what? Well, I'll leave the ds alone for a moment. But this magnitude of this first vector means it's just the number 1. Okay, that's why I said it's nice to write the cross product this way so that these numbers give us the strength of the magnetic field, and this really gives us the direction. And so you can see the number 1, it just kind of falls out. This one's worth mentioning. What's the angle here? Yeah, it's 90 degrees. And so again, I'll point it out here, but if the current at the top is going towards you, and we're looking at the field straight down towards the center, it's 90 degrees. And everywhere around here, it's 90 degrees. And so that one falls out of the equation also at sine of 90 degrees, which is 1. And so what I get is this 4 pi, and I think I wrote it as capital R, and I should too write it maybe more as a capital R to indicate that this is the R representing the distance away in general, but for this specific case, that distance away is the radius of this ring. This then becomes an easy integral. This is just what you might call a line integral, but it's the easiest line integral you'll ever do, right? It's add up all the little DS's. If you add up all the DS's, don't you get the total DS, right? The total sum around this? And we already know the sum around a ring. It is 2 pi r, right? That's the circumference of a ring. And so the 2 pi cancels with a 2 pi, leaving a 2. An r cancels with an r, and where we left off on Thursday was this then for the magnetic field at the center. And now we see A, its direction, and B, we see its calculated strength. Yeah.
How do you get magnitude of r hat?
No. The definition of an r hat is a vector of length 1. So it has length 1. It is a unit vector. So I know names aren't always so obvious, but unit vector means just that. 1 unit. Just like a 2-liter bottle means 2 liters. All right. Okay. So I told you guys this story, right? The the final, Physics 121? No? The meter stick? Yeah, a student came up to me at the end and said, I would have nailed that whole final. I did really well. It's the last one. I just missed the last part because if I just knew how long that meter stick was, I could have finished the problem. Yeah, okay. That wasn't you? No. Did you go to the Ducks game?
No, I didn't.
Oh, okay, good. All right, so anyway, so there's our first calculation. Yeah, I saw you in class Thursday. You said you were going, and I was like, oh, okay. But let's expand on this. Now, starting with the other direction. What would be different in this calculation if, instead of the current, if I was holding it here, and the current was going this way, what if the current was going the other way? Right. Hopefully you can see that the strength is going to be all the same, except now the direction is going to be different because my DS would be pointing this way into the board. The DR would be down here, so if I took my right hand and put my fingers towards the DS and closed it to the DR, I would get pointing over to this side of the room. And so I get the same number, I just get a different direction. Yeah. Oh, you definitely could. Remember now, if this was a proton, say, going towards you, and the current was going this way, which we said would make a magnetic field, then if I go V cross B, that would be a cross product of up. Did I say electron or proton? Proton, okay. So the proton would be deflected up. But if the current had been going the other way, then the magnetic field would be going this way. Then that proton, as it goes through, would be V, but B would be that way, so V cross B would be down, so a moving proton would deflect down. So I'm not sure what you meant by that, but the direction of the magnetic field is crucial because the deflection of that moving proton would change depending on the direction of that magnetic field. But that right angle is either up or down, and it's a different direction. So the direction of the magnetic field matters. Yeah. But with all that said, I want to give you a clever and useful second right-hand rule. Now, this is not the right-hand rule for vector cross products. This is the right-hand rule to tell me what direction is the magnetic field in this ring. Now, I only calculated it in the center. I think you would agree that the magnetic field would be in the same direction everywhere within here. It would just be a little harder to calculate if it wasn't in the center. So good news is we won't do it anywhere but right at the center or along this axis of symmetry. Okay? But conceptually, we can always say that the magnetic field would be pointing towards the computer if the current was going in this way. And here's a real easy way to do it. It starts with your right hand again. That's why we call it a right-hand rule. But don't confuse it with a vector cross product. But if you make a little fist, thumb out, look at my fingers. Don't my fingers curl in a particular direction? Let me hold my right hand with my fingers curled in the same direction the current is going. Which way is my thumb pointing? In the direction of the magnetic field. What if the current was going the other way? No, I guess I could hold my right hand with my fingers curled in the direction the current is going. And so use your fingers as the direction of the current here with your thumb out, and that will help you decide right away which way the current is going. Or you could always come back to the right-hand rule for vector cross product, because that's, of course, where it ultimately came from to begin with. So if you want to learn a new one, and I would encourage you to, fine, just don't get it confused with vector cross products. So we have the right-hand rule for vector cross products, where we put our fingers into the first vector, we close it towards the second one. Here, we just start with them curled. So if the current's going around, hey, magnetic field's that way. This way, hey, magnetic field's that way. And so anytime we have current going in a loop or a partial of a loop, we could easily, hopefully, point out what direction is the field by taking our right hand and holding our right hand with our fingers curled in the same direction the current is going, and then our thumb will give us the magnetic field. And so that becomes a very useful technique. The only challenging part is that it is a different right-hand rule. So don't just say the right-hand rule. Say the right-hand rule for finding the magnetic field in a loop. Kind of long, I know. But at least that will keep us from getting it confused with the right-hand rule for vector cross products. And another right-hand rule that we're about to incorporate here in just a second. All right? Well, now let's start something new. What if I didn't have a full circle? What if it was only part way, like an arc? How would all this change? Would it change? And I guess simply what I'm asking is, with a different geometry, could you tell me the magnetic field at the center of an arc instead of a full circle? Well, I would say it would be half only if the arc is half a circle. So if you're doing a semicircle, sure, it's half as much. And what if it's a quarter of a circle?
Find the arc length.
Right. So if it is from an arc, and as you pointed out, if it's a full circle, I would expect this. If it's a half a circle, well, then it would be half that much. But isn't that really what this step was all about here? Wouldn't everything be the same all the way through here? But when we got to here, what would be the difference? Yeah, you would not go the whole full circle, right? You would go a fraction of a circle. And so, you would have a fraction of a circle. Maybe I should actually just backtrack all the way to what I have right there, which is mu naught I over 4 pi capital R squared. That's that part. And then maybe I'll just write it as S for a fraction of a circle. Well, let's look at an arc here. let's say I have an arc where this is some radius, and then maybe I have some current I right there, and then this is some angle. How do I get that arc length S? Yeah, and I'm going to use a very useful relationship. It's useful only if you measure angle in radians. I want to point that out. But the arc length is the angle times that radius. So if I take advantage of that and put it into here, then I get mu I theta r 4 pi, another r squared, and at least the r's cancel off. And so for an arc, anyways, I get this relationship. And so what is the magnetic field from an arc? And maybe I better just confirm 4 pi r, yeah, that's what I got in my notes there. All right. So I would do basically the same. What if, on the other hand, I did another full circle, but let me look at a different picture. One that I would say is a bit more sophisticated, if you will. Let's go off the center. Could you tell me the magnetic field there? In fact, let me just expand this. Could you tell me the magnetic field for any geometric shape? Could you do a square? Could you do a rectangle? Could you do an ellipse? Could you do? And so before we spend too much time here, because we do have to move on to other things, hopefully you're seeing the point. Don't I just have to do this integral, right? Along the path where the current is. And of course, it's going to get different values for different scenarios. But now, let's do a circle, but you are off center a little bit. And I must admit, this one is a bit harder than the circle and the arc. In fact, I would classify this, that the arc is really the same as the circle. The arc is just a fraction of a circle, or maybe the other way around. You could say the circle is a subset of the arc, right? But I'll even go that one step further. Calculating it off axis will probably give me an equation that is related to x. And if x is equal to 0, then wouldn't I be at the center of the circle? And so for those of you who've had a chance to read the book, you'll notice that your author actually does this picture first before he does the circle. He just says, look, the circle's just a special case, but I thought I would do the circle first because it's an easier case than the one that's out of the center. But let's look at this one and say, all right, how do I calculate the magnetic field at a point P? Okay, so here's a point P. That is a distance x from the center. The ring has a radius of a. How do you get the magnetic field? Well, again, if I can get nothing else across here in this first hour, it is you will always get the magnetic field by adding up the little chunks of current that create the magnetic field. And so that was the lesson that we learned for electric field with Coulomb's law in chapter 23, and that's the analogy that I'm trying to get across here in the first half of this chapter. Right? It's just, what do we know? We know the magnetic field from a single chunk, so add it up from all the chunks, and hopefully the integral is reasonable to do and not too hard to do. But again, like we did in chapter 23, I need to emphasize that half the problem is really done by looking at the geometry and reading the physics, not so much doing the integral. And so that's real important. I'll start with direction, because I think your author does a really good job here. And I brought out the ring and the ruler and a little pen here to hopefully kind of illustrate the same thing that your author is trying to say here, is let's start with a little ring. And in this case, he's got a ring, and he says the current here is ds. He says that's along the z-axis to get started. So I'm going to hold this in front of you in kind of a 3-dimension, and maybe hold it right here. This is the little current going towards you. Okay? So there's the z direction, towards you. The x direction is along the axis of symmetry. In fact, so you can have something to look at. Maybe I will use the corner of this desk right here. This is the x-axis. And so I will put it right at the center of the ring. So if I hold this ring right about here, the x-axis is hitting right about the center. And what he's trying to say in this picture is there's some point P, maybe right about here. That point P, there would be a magnetic field that is created from the sum of all the chunks around this loop. And let's just look at a little piece first. Let's look at this little piece at the top. This little piece at the top, which has current going towards you, would create a magnetic field at this point P in what direction? Good. You guys are picking up your right hand, and you're going to do a cross product. Right? And so let's do the direction first. The first part of this is to find out, well, which direction is ds and which direction is dr. So what direction is ds? Okay, towards you. What direction is dr? And I'm hoping you can see it's angled down a little bit. That's why I brought the ruler out, thinking, okay, look, the chunk is above the x-axis, and so r hat is down at a little angle, isn't it? So it's not just simply straight across towards the door. Okay? And so if I were to take my right hand and put my fingers towards you, the ds, and kind of rotate it a little bit so I can close it towards the dr. Right? There's my dr. Which way's my thumb? And that's why I got the pin there. There's the magnetic field. So I think this is the harder one to visualize than any of the ones we've done so far, but that would be the direction of the magnetic field from that little chunk. And that's what your author is trying to show right here. He's trying to say, look, right there, there would be the magnetic field, a little magnetic field. He's saying it's angled at some angle theta from the x-axis. Okay, well, I'll show it to you again. There it is, right? Something like that. There's an angle between this desktop and that pin. That's what he's calling theta. Now the reason I point that out is because now, keep in mind, to get the total magnetic field, don't we have to add all the way around this? And so maybe look at the one at the bottom. Down here at the bottom, what direction is the magnetic field down at the bottom? Or I should say the direction of the magnetic field from the current down at the bottom. So from this current down here, what would be the direction of the magnetic field here? Yeah, down at an angle theta, right? So what would happen to what your author calls the perpendicular components, the vertical components? Yeah, they're going to cancel. So good for us. We can figure out, without doing any math, just from the symmetry of it, that if we had all the way around here, all these little chunks of charges, that the magnetic field would look a little bit like this. That there would be a magnetic field from the first one that would point up at an angle, and another one at an angle, and another one at an angle, another one at an angle, another one at an angle, another one at an angle. And as we add it up, it would kind of look like all those little vectors together would make kind of a cone. But the neat thing about a cone is that means some of them are pointing up and some of them are pointing down. Those are going to cancel. Some of them are pointing out, some of them are pointing in. Those are going to cancel. And so as I go to add this up, the first thing I realize is BY is 0 and BZ is 0. Yay, I'm 2/3 done. Finding the magnetic fields, right? Y and Z component are just going to go away. Yeah.
So is the maximum magnetic field right up to 7?
Oh, well, we can ask that question in just a second. Let's find an equation and then maximize it, sure. But this dx, or the bx, does not cancel off. And so bx is the summation of all the little x components, which is db cosine theta. Fair enough? And so, again, like we did with Coulomb's law, here's our goal. Our goal is to find the total field. We have to add up x's with x's and y's with y's and z's with z's. And so any symmetry goes away. But in this case, our x components can all add together.
The angle that the field is coming off the x-axis, the same angle that the dr is coming off the ring?
Oh, the answer to it is yes, although I haven't shown that to you yet, but you can see it in the picture that that theta and that theta are the same. But let me work to that. Now, I will prove that to you. But at this point, I don't want you to even see that one. I just want you to see that all I'm doing is saying that I need to do step 1, what's the magnitude of the field, and step 2, multiplied by cosine of theta. Now, if I just add those up, I will get the total field. And so I will start with this statement. Let's get the magnitude. I'll leave the cosine theta alone here, but let's get the magnitude. The magnitude is what this was all about. It was a mu naught, an I, a 4 pi r squared, and then a cross product. And maybe I should have given myself a little more room to write the cross product here, because I want a ds magnitude, an r hat magnitude, a sine of the angle between them, not to be confused with the cosine of theta. And I really wanted to stop here and pause. And I ask it again, where did that cosine theta come from?
So you can find it.
Yeah, the cosine theta came from the geometry, right? It came from the fact that I was looking at an angle between the direction of the magnetic field and the x-axis. Where did the sine theta 2 come from? Yeah, this is a cross product. When we go to calculate the magnitude of a cross product, we got the magnitude of the first times the magnitude of the second times the sine of the angle between them. These are not the same angles. And if you don't see that, you might accidentally put those are the same angles there. If you did, you're going to make it a lot harder to do, because this one's actually pretty easy. What is theta 2 here? Yeah, and I'm hoping you'll see that, especially in this first one, we're looking at the ds that way and the dr is that way. There is a 90 degrees here. Now, granted, it's not a 90 degrees level, it's a 90 degrees at an angled plane, but it is still 90 degrees. And if I did it here, it would still be 90 degrees. And if I did it down here, it would still be 90 degrees. And sine of 90 degrees is just 1. And so that's going to just disappear in my equation. Okay? And so that's really kind of nice there. All right, let me leave my cosine theta alone. And that's why I didn't really want to label it as theta 1 and then theta 2. But I did at that step only to show you those are two different angles. One of them is 90 degrees. The other is not 90 degrees. It's something I got to still think about, but it's shown in this picture here. Okay, now let's look at some of these other terms here. As we add around the ring, anything a constant? Well, I'd say the current is a constant in that ring, right? We have no nodes for the current to split off, so that's a one big series loop, if you will. Okay, so there's our, chapter 27 about the current in a series. Anything else that's a constant? Yeah, the 4 pi. What about the R? Okay, what is the R? Okay, good. So R is a constant, and R is that distance from the current source out to the point P. And so in this picture, they're showing it along here. This is R, which, of course, using Pythagorean's theorem, could be written as the x-axis and the radius a. So as many of you are pointing out, I could write this then as an x squared plus an a squared and pull it in front of the integral. So yeah, completely agreed. So all those are a constant. Then I have the ds. The magnitude of r hat is 1. The sine of 90 is 1. And then I have cosine of theta. All right. So far, so good. Well, let me keep going. How about this angle theta? Is it a constant? And how would I write it in terms of parameters up there?
X divided by R.
Yeah, and so now we need do a little geometry that you noticed earlier. If you look and call this the angle theta, and realize that there is 90 degrees between this r vector and the magnetic field, so 90 degrees. That means this little angle right there would be the complement of this one, right? This would be 90 degrees minus theta. And of course, we're making a right triangle, so that angle is the complement of that angle, which means we're back to theta again. And so, as you noticed, there is an angle theta up here, and it is the same angle as that theta. So, coming back to this picture, here's what that is trying to say, that as the magnetic field is tilted at some angle theta from the x-axis, that angle theta is the same as the angle made down under here. Okay? And I can then write that, knowing that this is theta. What is the cosine of theta? Well, it would be the adjacent, which is A, over the hypotenuse, which is R. And so I can write this as A over the hypotenuse. And let me write the hypotenuse with Pythagorean's theorem like we did there. And so that's cosine theta ds. And as some of you already pointed out, that too is a constant. So not only can we write it that way, we can pull it out. Yeah.
What is theta 2 again?
What's what?
Theta 2?
Theta 2 was the angle that I got from the cross product, which is 90 degrees. Whereas theta 1 is the angle I got by looking at the direction of the magnetic field, and what angle is it with the x-axis, getting the x component. And so when I pull this out to the other side, I get a mu naught, an I, an a 4 pi, an x squared plus an a squared to the 3/2 power, and an integral of ds. Yeah, it's an easy line integral. So, like you'll see us do again and again, we won't have any tough line integrals, like I'm sure many of you have seen some hard line integrals in math. I don't know which one it is. It's 200. You do a lot of integrals. And again, the intent there is to show you how to do some hard integrals. That's not the intent here. And so like Coulomb's law, most of our integrals actually came down to be something pretty simple. The hardest part was not so much the integral. The hard part was, did you recognize that angle, that angle? Did you recognize these were a constant? Did you recognize what ds is? Did you recognize that this has unit of 1? Did you recognize blah, 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 blah? Okay? And so it's a lot more about reading and understanding the meaning behind the math than it is actually some tough integrals. Don't worry, your day for tough integrals is coming. That's what you'll do when you take your next D&M class. You'll put together, you'll come in and your teacher will say, hey, remember all that great magnetic field stuff you learned in Physics 122? And remember all that great math you learned in Physics 200? Let's put them together. And so just like I'm saying, let's take our Calculus 150 and our Physics from 102 and kind of merge them together. And so that's kind of level we're at. You'll go to the next level. We call this peeling the onion as far as learning goes. So we learn one layer at a time. We don't do you know, anything more than we learn a little bit about everything all the way around. We take the first layer off, we go to the next one. And so we teach you a little bit about magnetism in physics, whatever. Then we teach you a little more in physics 122. And then we teach you a little bit more as an upper division, and a little bit more as a master's student, and a little bit more as a PhD student, and a little bit more as a postdoc student, and a little bit more as you get the Nobel Prize. Yeah.
Wait. Oh yeah, so explain to me the sine equals 9, the sine equals 1 thing.
Sine equals 1. 90 degrees.
Sine, like sine sub, like sine, sine 2 theta 2, theta 2.
Theta 2 is the angle between these two vectors, ds and r. Right there.
So if you look at the ring straight ahead, you will see like it's 90 degrees like that.
Well, 90 degrees. I don't know. It's going this way. And so maybe I should think of it as, here's something going straight out. I got a meter stick going straight out, right? And I take the r vector that, it's not straight out, but it's angled down. And so if I think about a plane coming up here, there's a 90 degree bend in here. Yeah.
So it's an XZ plane?
No, it's the angle between that black line and that blue line, 90 degrees. So it's the angle between the z-axis and a plane that is sloped, crossing the x-axis here and sloped up and crossing the y-axis there. Yeah. Mm-hmm.
How do you know which angle to look at to not get mixed up?
Because I know that this is the angle between the x-axis because I'm looking for the x component. I know this is the angle between ds and r because I came from the cross product. And so the way to answer it is I know where it came from.
Is it always 90?
No, it's not always 90. It has been 90 when the easy ones I've done.
So why doesn't it replace it? So it's going to replace the circumference?
Oh yeah, so if you want me to continue on, I will. But there are some good questions I needed to answer. Okay. And so now the next step is to actually do the integral, which, as many of you are already pointing out, is going to be a simple integral. It is just ds. ds means add up all the current. That's just around the ring. And around the ring is 2 pi, and in this case a, since we're talking about a being the radius of the ring instead of the capital R. And so a 2 pi cancels off, and an a goes without one. And so we finish up with the equation, and certainly the hardest one we've done so far. And maybe even the hardest we'll do in this category. I don't know. The next one we do is not so easy either. But we get a mu naught times I times a squared times a 2 times an x plus an a squared to the 3/2 power. And so there would be a more generalized formula. That is the magnetic field along the axis of symmetry. Okay? And I can get the direction the same way here. Because what direction is this? Along the x-axis, right? Take your right hand, put it on the ring, curl your fingers. Which way is your thumb pointing? Along the x-axis. And so use that little quick trick to figure out what the direction is the magnetic field. It's what I call the second right-hand rule here. Okay? Not the cross product one, but the one where we can find the direction of the magnetic field. Yeah.
That sine of theta 2 is 90 degrees because of the location of P, right? You move P over off of the center.
No. If I were to change P,
Move it left to right.
okay, here.
No, move it left to right.
Oh, off the axis.
Yeah.
Oh, yeah, if it was off the axis. Oh, right. And that's exactly what you will do next year, is to move it off axis. Because if I move it off axis, then I don't have something as simple as 90 degrees. It shows up in my line integral, and I've got a hard line integral to do.
But not this year.
And so that's where I need to dive into my Math 200, right? And so that's what I meant by saying, your day is coming. We're not there yet, but we're one step at a time, one layer of our onion, and you will do you know, some significant line integrals in the future. And I should even point out, depends on your major, because I'm not sure every major who's in here now will also be taking an upper E&M. Obviously, you guys who go into electrical engineer or physics, you will, but I'm guessing that you civil engineers probably don't take an advanced E&M. I'm not completely sure on that, but that would be my guess. So some of you are shaking your head like, good, good, but yeah.
Can you explain to me why y equals a, y is a because x over r?
This is the angle cosine right here. Cosine is the adjacent A. Adjacent over hypotenuse.
Law is the other way around. It was the angle between the x and the r.
Yes, because in Coulomb's law, we define theta to be this angle. Now we've defined theta to be here, which then we have shown that becomes the same as that one. So it just worked out different. I mean, I wish every step was identical in Coulomb's law. The concept is the same, but because of the cross product, we end up with different angles, and we just got to read along and understand what each step means. Yeah.
You said you were going to confirm that the maximum is...
Right, so you asked earlier about where is the maximum. So what I have done, as you pointed out, is I've only calculated the magnetic field along the axis of symmetry. And so I can only use that formula for along the axis of symmetry. And we won't be getting off the axis of symmetry this semester. So anywhere along this axis of symmetry, it is valid, including at the center where x is equals to 0. So looking at this equation, where would the magnetic field be the strongest? Yeah, and you could even see it. Some of you are suggesting take the derivative, but I don't think it's that necessary to take the derivative even. This function is going to get its maximum when the denominator is the smallest. The denominator is the smallest when x equals to 0. And so at center, maybe I'll even put at center, x is equal to 0. And so B becomes mu naught times I over 2. When I put in x equals to 0, I have a squared, square root of that, cubed, canceling with that, and I just get a. And I get exactly the same formula we just did a half hour ago for what is the magnetic field at the center. And of course, it was a much easier calculation. You might argue that I didn't even need to do that first calculation. I could just derive it from here. And although I would agree with that now, I think I needed to build you up. I didn't want this to be your first calculation.
But it wouldn't be a specific direction. It will be either coming in or out.
Well, okay, now remember, this, of course, is a formula giving you the magnitude. We have right here at this step sacrificed anything about direction by putting in the magnitude of the cross product. So from here forward, we only have an equation telling me the magnitude. You got to get the direction by taking your right hand and curling it in the direction of the current. Or if the current was going the other way, curl it that way. So you are going to have to figure out both its magnitude and its direction. This just gave me magnitude. I'm telling you, get direction by curling your fingers.
But when you do the sine theta, that will still be 1 because the angle is 90 between A and the ds. And then you don't have a cosine, it's 0.
What? For what? The current goes the other way?
For that force that's coming, that's in the middle, that's in the center.
Okay, fair enough. If I was in the center, it would be an easier calculation because there would be no theta involved. That's why I did it first, because I didn't have a theta to worry about. But the theta is buried in the x, and so when you put the x equals to 0, you can see it comes out to be the same.
So there's no one direction for the magnetic field, but there's a direction for the force.
No, yes, there is one direction. The direction of the magnetic field would be along the x-axis. And if I was even on this side, it would be along the x-axis.
No, I'm saying the one that's in the middle.
It's along the x-axis.
Still.
Oh, yes.
0, 0.
No, it's not 0.
No, I mean 0 at the x-axis. At point 0 of the x-axis.
So when it's at 0.
Oh, cosine of 0 is 1. The field is not 0.
So you get a magnitude, yeah.
Yes, yes, you get a field.
On.
All right. Okay, good. Well, I'm going to keep going because I know this takes a long time to set in. That's why I really didn't want to have the test 2 days from today. I didn't want to show you this on Tuesday and test you on Thursday because this does take a while to sit in and to settle in. So you got 9 days to keep this, straight. And I didn't expect this first most significant one to be the all answer. So let's do it again. Let's do a different geometry, same idea. Let's get the magnetic field yet again, but this time not from a loop. Let's just do a straight piece of wire. And so let me change the picture here. Yeah, let me change the picture. And actually, let me try picture number 2 here for a moment. And I will grab this wire now and think of this as the current. So instead of having the ring, I will have this current. Okay? Now, obviously, you can see some limitations with this. The current must have come from somewhere, and it must go somewhere. But more on that later. But let's just look at a section of wire that's straight. Because who knows the other part that it came from. So the total field is going to be a combination of all the currents. I agree. But for starters here, let's just look at this section. And let me start with the easiest one. A. What is the magnetic field
0.
at point A from this long straight wire?
Sine theta is sine 0, 0.
Good. A lot of you are seeing it. It's 0. Why is it 0? That should be the easiest one. Right. Back here in the cross product, when I start to work it out, and I will in a minute, the magnetic field, the strength of the magnetic field is based on this cross product. And in this case, point A, if you look at a little chunk right here, ds is this way and r hat is that way. They're in the same direction. So how much of a field do you get at point A from here? 0. And that would be true for every little chunk. And so the field along the direction of the wire would be 0. Ha! Wasn't that an easy one to do? And in fact, why don't I look at this picture here for a second before I look at the other points, A and B. How about we look then at figure 5? What if I am the design engineer here, the electrical engineer, the material science, the physicist, whatever, and I'm trying to build a microprocessor. And I know this, that my transistor and the speed of my transistor is affected by the strength of the magnetic field. I either want a large field or maybe no field. I don't know. But whatever it is, I have a little transistor. Let's put this transistor at point O. For better or worse, near that little transistor, within micrometers, are hundreds of other little currents flowing around in my microprocessor. And I want to control how strong the magnetic field is for that transistor. And so I design a current that kind of has this shape. Why? How much magnetic field do I get from A prime to A at point O? 0, exactly. And so that was the cleverness of this design. That I can have a lot of current, I can have a little current, it doesn't matter how much current, the magnetic field is 0 because of the current. At least at that point. I mean, other points it's different. And so building this whole processor is not going to be simple. But at least at point O, I can control the magnetic field by saying I'm going to get no magnetic field at point O from that part of it. And the same thing can be said about C to C prime. How much magnetic field do you get from that one? None. How about from A to C? Do you get a magnetic field? Mm-hmm. And that one we already did. Didn't we do the arc a moment ago? It was this times 2 pi, or theta over 2 pi, to get the arc. And so the magnetic field from the arc would be mu naught times I over 2a, well, maybe I should write it like they do, 4 pi a times theta. And I don't have any numbers necessarily here to work with, but if they were to tell me, and I think this is the first example of an arc in your book, I think they tell you it's something like 30 degrees here. And so converting it into radians here, I could put that number into there, I can put the current, I can put the distance away, which in our case would be A, if they have it labeled, and I can get the magnetic field. And so this current that came in, went around an arc and went out, does affect the magnetic field at point O. But the lesson I wanted you to get was only the arc part, not the straight line parts, are affecting the magnetic field. And what direction is the magnetic field at point O?
In the board.
Good, into the board. I would take my right hand and I would curl my fingers in the direction of the current. And my thumb will give me the direction. And so the direction of the magnetic field at point O is into the board, into the screen, because of the current. And it's all calculated based on the arc, not the straight wire. However, let's look at those other points next to that long straight wire. Let's go back to this picture. How about B and C? Okay, so it's not 0? No. Can we calculate it? Yeah, let's do it. But let's start with direction. What direction would the magnetic field at point B be? Right, and so what we're about to do is we are about to start all over right here with a summation. We are going to add up the little chunks of charge along that line. And maybe one of the first things to talk about is direction. What direction is the magnetic field? And we can get that from our cross products. The ds cross r hat. So if we look at this little chunk right here, say we want to know the magnetic field at B, ds is this way. Which direction is r hat? Up this way. So I take my right hand and I go ds cross r and I get out. I can do the same thing for this little chunk. ds would be this way, r hat would be kind of at an angle, looks like greater than 90 degrees, but it would still give me out. How about this little chunk? Out. How about this little chunk? Out. And so at point B, every little chunk of charge is always going to give me out. So of course the total result is going to be out. And I'm hoping you'll see that everywhere up here, at point C also, it would be out. Yeah.
Isn't there another right-hand rule where your thumb is the direction of the current?
Ah. Give me 30 seconds. Let's look at the field below. What direction is the field below? In. And so let me give you another right-hand rule. That might give us a nice little trick for finding the direction of the magnetic field from a wire. So now let me refresh here. Okay? The right-hand rule that we've been doing a lot in the last chapter and started in this chapter was cross products. Right? You put your fingers in the direction of the first vector, you close it towards the second, and your thumb gives you the direction. That's what I call the right-hand rule for vector cross products. True. The second right-hand rule that I gave you today was a little trick for finding the direction of the magnetic field from a ring. Let me give you another right-hand rule, the third one, which is a little trick for finding the magnetic field from a straight wire. Take the same configuration, but this time let your thumb represent the current. Now I say this time because remember last time when we did the ring, My fingers represented the current, right? And my thumb gave me the field. So for this one, we're going to switch roles. We're going to take that same configuration, but we're going to let our thumb be the current. Kind of makes sense. Your thumb makes a straight line. Your fingers make a ring. But if you hold this in the direction of the current, look closely at your fingers now. Your fingers will get you the field. What do you notice about your fingers here at the top of the wire? They're coming out. Same direction as the magnetic field. What direction are your fingers pointing down here? In. And so our third right-hand rule is a way to get the direction of the field again. We can get the direction of the field from a straight wire. Okay, so we have two new right-hand rules for today. First one is, can we get the magnetic field from a loop? Yes. Use your fingers for the current and your thumb will give you the field. Reverse that for this one. Can I get the direction of the magnetic field for a straight wire? Yes. Use your same right hand. Use your same fist with your thumb out. But now, switch the roles. Let your thumb be the direction of the current. And your fingers will give you the direction of the field. So you can see why those two ones can get mixed up because they are so close. One of them, you are letting your fingers be the current and your thumb be the field. The other one, you're letting your thumb be the current and your fingers be the field. But the best thing to remember is just match the geometry. If you got circles, use your fingers as current. If you have straight lines, use your thumb as current and your fingers will give you the field. And that's the way I find it easy to remember is look at the geometry I have. Yeah.
Is it safe to say that I and B are always perpendicular to each other?
Yes, yes it is safe to say that I and B are always perpendicular, and that's what we mean by cross products right there, right? The cross product is always perpendicular to the plane that is made up by those two. Yeah.
Are those two right-hand rules interchangeable or not?
You could maybe argue that they are one and the same, but I think it's kind of simplest just to say, because they all came from right here, right? I mean, you really could just learn this and you're done with it, because everything came from just adding this up. And so if you only want to do one right-hand rule, do this one, do the cross product, you can figure out the direction. The other two that I'm showing you are just kind of quick summaries of a long integral.
What was the first one again? The fingers or the...
Fingers are current, thumb is field. Second one, thumb is current, fingers are field. So just reverse roles. So your thumb is the direction current. So above the wire, the field is out. Below the wire, the field is in. Ah.
Is that
What about out here? Huh?
is that like the field is circular?
Right. And I haven't got that far in the calculation, but I might as well bring it up now. There's nothing unique about this plane. So what about the field out in front? Be down, right? My fingers are pointing down. And then we're going to get a circle for the field around here. The top part is pointing out. Bottom part is pointing down. And the same logic that gave us out and down, we could think of this whole plane then rotated forward. And so that would make in front of you down and behind you up. And we could rotate it a little bit and we'd get circles all the way around here. And so what we will soon discover here is that there is a magnetic field at point B and C, not A, and that it will be making circles as we go around here. So let's actually do a calculation. But let me switch pictures so we have a little more geometry to work with. And I'm going to actually grab a picture that I think your author should have continued in this edition of the book. And so I'm going to show a picture that's not quite in your book, and then I'll get to the one that's in your book. I'll build up to it. But let's do this for a moment. let's calculate then the magnetic field at point P from this long straight wire. Okay? And so this, I think, is the hardest of our calculations, but not unreasonable. Not at all. But again, like the last one, we have to understand what each piece is. So again, I didn't expect you to understand each meaning of each piece the first time, but let's see if you can add to that the second time here. All right, so here's what I'm going to do, is I'm going to imagine myself adding up from back here going forward. And this is going to be the x-axis, and this is going to be the y-axis. So over here would be negative values of x, over here would be positive values of x. The current is going to the right, so this would be the ds. And so ds would be along the x direction. Okay? And so as I come over here, and maybe the first thing to ask when I do this is, what stays the same along this integral? Well, hopefully the first obvious is the mu naught and the 2 pi. Those are all constants. They're always constants. All right, I'm going to pull those out in front. But hopefully another one that stays the same is the current. So there's no increase or decrease in the current here. Okay, so that one's pretty good. R. Is R a constant? No, it's not, right? R is, of course, this distance from the little chunk out to there, and labeled in this picture, that is R. And so you can see that R is getting smaller, 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 and the smallest here, and then bigger, 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 bigger there. So one thing I want you to catch from all this is, looking at the magnetic field at point P, which part of the wire contributes the most? I mean, all the wire contributes to the field, no doubt. But what contributes the most, and why? Right here at the origin, right? Isn't that the shortest distance away? And what else? And it's 90 degrees, right? And so as we are back here or up here, not only are we further away, but the angle is less than 90 degrees. And so the magnitude of the field is contributed not only from by how far away you are, but what angle it is. And so that's why we can kind of say, hey, if you have a long wire, that's great, but really, what about that little section that's real close and perpendicular from it? That's the most significant part. And that's what we see in the math here. All right, so R is a constant. I mean, R is something that is changing. It's a variable. So I'm going to have to leave that alone. So I'll put the R there. Okay. Let's talk about direction again, and then the cross product. You already told me about direction, but it's probably worth mentioning it again. What direction is the magnetic field at point P from that chunk, from that chunk, from that chunk, from that chunk? Aren't they all out? Okay, so they're all out, which in this picture would represent the Z direction here. So I'm not going to really say too much about Z or X, because when we do a problem, it may, be, on our problem it may be different, but isn't it out of the screen? Okay, and we can use our third right-hand rule to find out whether it's out or it's in, depending if it's above or below. Okay, so I'll just put B, and this is the magnitude. So I'm going to get the direction by doing my right-hand rule, but I'm going to get the magnitude by taking the cross product. So that's ds times the magnitude times the sine of the angle between them. Now, let's look at that angle. What's the angle between them, and does it change? Yeah, it does. Dang it. Not so easy this time, right? But this is why I like this picture, and your author did not include it in the 7th or higher editions of the book, so I went back to the 6th edition to grab this one. But that's what he means here by theta. Theta is the angle between the ds and the r. And so when you're back here, you have one value of theta. When you get to here, it's 90 degrees. And when you get to here, it's starting to get more than 90 degrees. Okay? Now, fortunately, the magnitude of r hat is 1. And fortunately, the ds, the current, is laid out along the x-axis. So that's dx. But the rest of the integral is not quite as simple, but I do have a dx, I have a sine of theta, and I have an r.
Couldn't you turn sine into a over r?
Yeah. And so now I have to do a little more sophisticated math than I've done in the past. You guys might notice this. This can be done really nice with some trig identities and can be simplified. And so that's where we're going to go. I think you can see that the angle and the r are somehow related, right? And the position is somehow related here. And so maybe I'll come over here on this little part of the screen and say, let's take a look at this. Why don't we do a little triangle right here? If I make a little triangle and I say, let's take a look at tangent of theta. Let's take a look at cosine of theta. Let's take a look at sine of theta. And I think maybe sine theta might be the one to look at first, because what does sine theta give me? A over r, right? And so this is A over r. Or written another way, r becomes A over sine theta. Okay, so if I make my first substitution here, dx sine theta, I can eliminate r by writing it as an a squared over a sine theta squared, which then means the a being a constant, maybe I should pause there, right? The a is the perpendicular distance away, and so as we add up, a doesn't change, but the angle does. And so that was the nice part about this step, is then I can go dx, and then I have sine cubed theta. So I have switched my r into a theta, and so my three variables, x, theta, and r, need to become one variable, and I've done at least the first step towards that, right? And so there's kind of that first step. The other nice step actually shows up with tangent of theta. Tangent of theta is what? Isn't it a over x? Close. It's a over the magnitude of x, isn't it? Is x a positive number or a negative number as shown here? Yeah, okay. So really, of course, when you do your tangent, you're talking about the magnitude of it. So using my x-axis, and this is the origin, I probably should write this more like tan of theta is equal to a over the negative of x. You see, that way, when x is a negative number, as shown here, I will get an angle that is what we would call the first quadrant. But when I get over to here, when x is now a positive number, then I would have the tangent of a negative number, which means it's greater than 90 degrees. And so to keep my signs straight here and not to mess up there, I got to see that little subtlety there. So don't miss that one. That's real easy to do there. But what's nice is, don't I have a connection now between x and theta, which is what I'm looking for. I want to get these the same. Yeah. Oh, no, just stretching. Okay. So I am going to write this as x equals, and I'll put the negative a, and I will put it upstairs so that I don't have to mess with taking a derivative with something downstairs. So I'll move x to this side, I'll move tangent downstairs, but then I'll call it a cotangent so that everything's upstairs, because eventually I want to take the derivative. So dx equals negative a times, and what's the derivative of cotangent? It's minus cosecant, isn't it? It's, yeah, cosecant, but it's a minus. So another minus, and then a cosecant squared of theta. And that's not one of the common ones. And in the interest of time, let me not work it out. But it does, and you can look in Appendix B. I'm pretty sure that's right. A lot of you are shaking your head. That's right, right? Yeah, okay. And of course that means then dx can be written as a cosecant squared of theta. And so now this integral, mu naught times I over 4 pi a squared becomes,
There's d theta, isn't it? Yeah.
oh, d theta, thank you. That's, yeah. All right. And so that becomes an a cosecant squared theta, a sine cubed theta d theta. Ah, boy did I get lucky here, right? Now it's an easy integral. Because what is cosecant? 1 over sine, right? So 2 of these will cancel with 2 of those. And even an a here will cancel with an a there. And so I will get sine theta d theta. Oh, yay. Isn't that an easy integral to do?
What would possibly make you think to go through that step of tan equals a?
Actually, I guess what really, you're right. The way it's written, I probably would have done more like this. To be quite honest, I probably would have, right here, done, I mean, if this was the first time I was doing it, I would have probably done and changed the ds to a dx right there. I probably would have written the r squared as an x squared plus an a squared. I probably would have written sine theta as an x, although to get my sign right, maybe a negative x over an r, right? Oh, a, thank you, a, right? Sine, a, yeah, a. And to be quite honest, that's what I would have done first, and I bet most of you would have done that first. But I would have stopped there and said, what did I learn in Math 160? Trig sub. So let's change these from x's back to thetas. Right? That's exactly what I would have done. So I'm just avoiding that by saying, well, let's just do thetas from the beginning. But to be quite honest, I agree that you may not have jumped on that from the beginning. You would have jumped on the fact that you would want to have gone Cartesian coordinates. And once you got to Cartesian coordinates, you would have realized this is your standard trig substitution simple integral. Yeah. And so you would have then done a substitution and been back to here. And then finished it up. All right. So, but nonetheless, let's finish our calculation and say mu naught I over 4 pi a. And now I have the integral of sine, which is great. What's the integral of sine? It's negative cosine, isn't it? 0, 1, yeah, negative cosine. Evaluated from what now? Yeah, and this is where maybe a new picture might be useful here. This would be kind of the limits, right? I would start from back here and call that theta 1, something that is less than 90 degrees. And I would continue on past the origin to something greater than 90 degrees. And I would have a theta 2. So this would become mu naught I over 4 pi a. And I'd have a minus cosine theta 2 minus a minus cosine theta 1, which may be better written as mu naught I 4 pi a cosine theta 2 minus cosine theta 1. Yay! Sorry, got too excited. Too early. 1, 2. Okay. Although I guess the nice thing, even if I mix them up, the magnitude's the same. And I'm going to get the direction by doing my right-hand rule anyway, so I'm not worried about that. Okay, now, let me keep going, because personally, I like this. But your author decides, for whatever reason, that those angles are not the best angles to work with. Now, personally, I do, because those angles tie directly back to the cross product, and that's why I wanted to teach it that way. But I must admit, a lot of the problems we're going to have are going to look something like this. You're going to have something like a square. What is the magnetic field in the center of the square? Okay, I guess your first step might be to say it's the same from every wire, so let's find it for one wire and multiply by 4. The straight wire we have, right? And we can either look at it at this angle, theta 1, and this angle, theta 2, or we can look at it from the angles at the top of the triangle. Your author has chosen, in the later editions of the book, to do the top of the triangle. So, let's do a quick switchola here. Let's go back to edition 7 and show you the geometry your author has. He calls those top angles theta 1 and theta 2.
There was one in the homework that's very hard to do that cosine thing. You have to go back to that.
Yeah, and so I got to admit, finding these angles does tend to be often a little bit simpler, that's what you're saying, than finding these angles. And I'm sure that's why he switched to that addition. So once we get the result, I think you are going to appreciate writing it in terms of those angles. But getting to the result, I think you would appreciate these angles. So that's why I wanted to derive it with these angles, but make one more step. And say this is the equation your author gets after a bunch of work. He says it is not cosine, but sine, because instead of looking at that angle and calling it theta 1, he calls that angle theta 1, and it's the complement. So the complement of the cosine function is the sine function. So the sine, the cosine becomes a sine. The other one's a little bit harder to see because this and this are really the supplement and then the complement. So it's not just as simple as going from cosine to sine. There is a change in sine because of the other 90 degrees. Instead of the complement, it's the complement and the supplement. And so here, should I put a plus sign? Or, and here's what your author does, so I want to do the same as your author. He leaves it as a minus sign, but defines theta 2 as a negative angle. Did you catch that? Because this is the part that I think really throws students off. That they're not really sure what he's defining as the angle. So let me say it again. If you're going to use this formula, if you use the signs, then you are using these angles. Okay? Any angle sweeping to the left is positive angles, and any angle sweeping to the right is negative angles. If you only want to use positive angles, as some books do, then they put a plus sign here, but that's not the way your book works, so I want to emphasize that. That he's calling that a negative angle. And these are the angles from the top. So, your choice. You can use the angles down at the bottom, which are the direct angles which come from the cross product, which, like I said, are directly tied to the derivation, and I like that. However, calculating these angles in a lot of the geometries are really nice. As you point out, you've tried these, and so calculating these are really nice. Just remember to put that in as a negative angle. That's my little warning for you. And so I'll put a box around it, and there it is. There's our grand finale. I think the hardest one we will do this semester here is what is the magnetic field from a long wire, or from a wire, yeah.
But isn't the theta 2 always going to be
No, no. Now, granted, the way I've drawn it, it looks like theta, well, all the pictures I've shown you so far, theta 2 has been a negative number. But please remember, there would be the same derivation and hence the same equation if it looked like this. What if my wire was from here to here and I ask you to find the point P there? So in that case, this would be A. This would be theta 1. This would be theta 2, and theta 2 would be treated as a positive number. Yeah.
For the final form, they have in a sine of theta 1 and sine of theta 2.
Yeah.
You're already assuming that theta 2 is a negative angle, so you are bringing out the negative sign outside, right? Because sine is an odd function.
No, no, no. Okay. Let's say, as I mentioned earlier, I'm going to do the square. Okay? So, what angle would theta 1 be? 45 degrees, right? What angle would theta 2 be? Minus 45 degrees. And so do a minus of a minus. Okay? So make sure that when you do your geometry in your problem and you call this 45, make sure you put it into your formula as negative 45. Yeah. So what you're essentially saying is this and this contribute the same amount, which kind of makes sense. It's symmetric. Mm-hmm. Yeah. Okay. All right. In fact, this is one of those dilemmas I've told you many times that I for the most part, I always like to use the same notation of the author, unless there's a good reason to deviate from the author. I don't like to do it, even if I don't think it's the best approach, because it doesn't do you any good if you see two different approaches. You look at your book, you look at your notes, and they're a little different, and it makes that hard for you. So that's why I want to finish with this. However, I think this one was worth it. I think this one was worth deriving in terms of the angle from the cross product and then coming up with it. Okay? Well, all that was getting to, let's say this. What if this is a really long wire? Very long. And when I'm talking long, I'm talking at least 2 or 3 centimeters, because we're in a microprocessor and we're only 1 or 2 microns away. So we're back to this whole idea of what do you mean by a long wire? Well, again, maybe this is the perimeter current that is supplying power to my processor, and so I've got a lot of current going in there. And so it's a good 2 centimeters of wire going from one side of the processor to the other. All that is a bus of 5 volts. And so there's a lot of current going down there, and I am really, really close to it. With that in mind, what would this angle be? Pretty close to 90 degrees, right? And so the magnetic field from this very long wire would probably start off to something that's very close to 90 degrees. And what would it finish at? Negative 90. So minus the sine of negative 90 degrees. And of course, what's sine of 90? 1. Sine of negative 90? Negative 1 with a negative. So together, that's a 2. And so the magnetic field from a really long wire would be something, of course, a little simpler since we put in the angle itself. And so this is what I might call the special case. Just like we had the special case. What is the magnetic field at the center of the ring? Well, we really knew it everywhere along the axis of symmetry, and then we could do what's at the center. And then likewise, I can do this. Can I get the magnetic field from a long wire? Yes. What if it's really, really long? Well, then I can approximate it as something like that. And so there's the magnetic field from a long, long wire. Well, we've done a lot of Biot-Savart. Let's actually apply it one time before we go anywhere here. Let me show you another picture. Now that we've done some good calculations, we could probably do a lot of different configurations. I mean, could you do something that looked like and this? That one here. What's the magnetic field in the center of the loop? Well, we'll hold off. We probably won't get around to doing it today, but couldn't you think of this as a long wire plus a ring? Don't we now do a ring? And don't we now do a long wire? Put them together. We're done. Right? What is it from that one? It is a long wire, a quarter of a circle, and a long wire. You might call a semi-infinite wire, a quarter circle, and a semi-infinite. Add them together. Yeah.
For the last one, do we have to worry about the small twist in the distance?
No. 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 We haven't done any. When the current's three-dimensional. Yeah. Although we could after we do Ampere's law a little bit, so we can build up to that. So I think you're getting the idea. And in fact, here is a case of. No, where'd it go? I guess it's this one here. No, not that one. Where does he apply? Ah, this one here. Just simple as this. Let's ask this question then. What if I have two wires, long wires, okay? And so very long wires, we'll keep it simple. Two very long wires, as shown, current 1, current 2. They're right next to each other, current going in the same direction. Again, maybe back to computer technology. This is a bunch of wires in our microprocessor, or this is a ribbon, a data ribbon, and we've got a bunch of lines of current right next to each other. Let's just look at two of them. Is there any interaction between these two? Well, let's take what we just learned together with last chapter. Watch, this is what it's trying to say. This green line is representing the magnetic field from wire number 2. Isn't wire number 2 making a magnetic field? I mean, let's represent its direction here for a second. Forget current number 1 is even there. But if I were to take my right hand and grab wire number 2 with my thumb in the direction of the current, the magnetic field would be in the direction of my fingers. And maybe it's time to emphasize a little bit more. You guys already brought it up. They would be circles around here. Because what we calculated was the strength of the magnetic field. Notice that the strength of the magnetic field depended on how far away you are. But it would be the same no matter what direction you went. And so if you went straight up from the wire, or straight out from the wire, or straight down from the wire, or straight back from the wire, it wouldn't matter what direction you went. Everything we did would come out to be the same, and you would get the same magnetic field. So the magnetic field always has the same strength given the same distance away. However, its direction would change. What we worked out in class is what direction would the magnetic field be above this wire, up here? Yeah, it's going to be out of the board, and that's what they're trying to say. Magnetic field from number 2 is out of the board. What direction would the magnetic field be down here below the wire? Into the board. What direction would the magnetic field be out in front of the screen? Down. How about over here behind the screen? Up. And so what we have is that we have a ring, like our fingers. We have a circle around it. And so that's what the author is trying to indicate with that green circle. That the magnetic field is making a circle around it. And the value of the magnetic field would be calculated like here. But go back a chapter. Look at that top wire, current number 1. What did we learn in the chapter before? If there's a current and the current is in the presence of a magnetic field, what happens?
Force.
There's a force on that wire. So this wire right here would have a current, I1. It would have a current in the presence of a magnetic field, which is created from wire number 2. And so for me to get the direction of the force, I would need to find out the right-hand rule for vector cross product. I would need to take my fingers and put them in the direction of the current. I would need to rotate my hand so I can close it towards the direction of the field. And in this case, I would get down. And so wire number 1 is being pulled down because of the magnetic field created from wire number 2. And so that's what I meant by, is there an interaction between these two? Yeah, these two wires are being sucked together. Newton's third law would say if wire number 2 puts a force on number 1 down, then wire number 1 puts a force on number 2 up. And maybe we can see that. It's not really shown in the drawing here, but what direction is the magnetic field at wire number 2 from wire number 1? So if I take my right hand and I grab it and I curl, the magnetic field's going into the screen. Current number 2 is going along this direction. The field is in. So if I take the cross product here, I got my fingers going in the direction. I close my finger inward towards the magnetic field. I get my thumb pointing up. So what direction is the force on this one? Up. Not a surprise, Newton's third law. And so these two wires are being pulled together. And so two wires with current in the same direction get pulled together. So do they have an interaction? Yes. And how strong is that interaction? Obviously depends on the current. And not just one, but both currents. Can we calculate it? Sure we can. Keep that in mind. And let's go back a chapter. If I go back a chapter and say, what is the force on a wire carrying a current? Well, let me calculate it based up here, because I guess I would write this then as current number 1 has a length of, what do they show? Little l, in a magnetic field which is created from wire number 2. And then in this case, sine of 90 degrees. And maybe I should pause here. This is last chapter. This is the angle between the current and the magnetic field right there. Current is that way, magnetic field is out of the board, cross product is down. And so wire number 1 is being pulled down. Okay? And it's being pulled down with a force equaling to current 1 times length times magnetic field B. But let me keep going, because now that we have just learned how to calculate the magnetic field from a long wire, this is going to come into play. This is how we get the value of the magnetic field. The value of the magnetic field comes from current number 2. So this would be mu naught times current number 2 over 2 pi. And should I write an A? A was the distance between them. How do they label it here? Oh, well, they label it as A there too, so no questions about it. We'll just label it as A. It's all right. I was just thinking, you don't need me to explain this. You can just ask Cirrus. How do I calculate the force between two wires? Yeah. Yeah, I've had, it's good at getting directions, but when you ask anything like what's the meaning of life, you know, or how do you, but I'm going to try the magnetic field one. Yeah, okay. But there it is. Let me just kind of rearrange it. I think your author writes it this way. Actually, I think he writes it this way. He puts force per length. And then puts a mu naught current 1, current 2 over the 2 pi a, I think is the final result that he writes it like that. And so that's the force per unit length. And so this we need to know how long our wire is, 2 centimeters, 3 centimeters, 1,000 centimeters, whatever. Okay. And so, but the point here is we can figure out there is an interaction, and like any tough problem, we've got to put this chapter with last chapter together to figure out the force between them. Yeah.
Are you assuming that the length of the second wire is infinite and the other one has an infinite?
Well, I guess when I use this right here, makes me obviously imply that this is a very long wire.
Compared to the first?
Well, really compared to the distance separating them. So that when I calculate, if I didn't have it a long wire, I'd have to come back to this step. So I could still do it if the wire was not infinitely long, but yes, when I use this, I'm assuming that wire number 2 is really long compared to the separation between them. Now, this one up here, this was true for any straight segment, so that doesn't necessarily imply that wire number 1 is infinitely long, too.
So when you multiply it to the length of the wire,
Yeah.
technically you're getting the sum of all the forces coming from
Yep.
all the way from going all the way.
Right, exactly.
It's not just one force at a particular point.
Right, you might even, I guess more technically you would call this, but again now we're getting into math 200 or more, 200, where we call this a double integral. Because really, in order to find the magnetic field, I had to add up all the sources that created the magnetic field. Then to get the total force, I had to add up the total length of that wire. And so I added up the bottom wire to get the total field in the presence of the first one, and then added up the total length of the one there. So it's really a double summation, a double integral, yeah.
So that's just the magnitude of
Oh, now that's just the magnitude. So again, a lot of these formulas we have, if you'll notice, I'm going to keep going back to my right hand to figure out direction. So I've got magnitude. That's the force between them. Whether they attract or repel is going to require me to look at the direction of the currents. As you just saw me say, that if the currents were going in the same direction, they would attract. Let me move to the next step. What if they were opposite currents? Yeah, and we would get a switch in their application. If one changed direction and the currents were in opposite direction, then they would repel each other. Now, if they were both switched in direction, then we would just go back to attraction again. And so if they're in the same direction, they attract. They're in opposite directions, they would repel. All right, well, the reason I want to take in just a few more moments anyways is to say, what about the other half of this chapter, which I haven't even really said anything about? We have Ampere's law too. And so we had all this great way of calculating the magnetic field, and we have, but that's only half the story. The other half is Ampere's law. So at least let's throw it out there. We won't do any of the hard calculations for Ampere's law quite yet, but at least let's kind of get it started. But we should have 2 methods for calculating the magnetic field, just like in the first 2 chapters of this book, we had the 2 methods here. And so when I started this class about 2 hours ago, I was saying, remember this, that Ampere's law is like Gauss's law. And so I'm going to try to use your memory from Gauss's law, the stuff we did for Gauss's law, to hopefully make Ampere's law a little bit easier, just like I was trying to use Coulomb's law to make the Biot-Savart one a little bit easier. And so in Gauss's law, we had this. We had, if you added up the electric field on a surface, and notice it had to be a closed surface, that would equal to the total charge that was inside that surface divided by epsilon naught. Anybody remember that? And everybody raise your hand. Good, yeah. Make me feel good. All right, so you all remember that calculation, right? And you're probably reviewing for the final by now anyway. All right. So, so there is the idea of Gauss's law. Well, Ampere's law is very similar. You are going to add up the magnetic field. It's going to be closed. Unfortunately, here's where it's a little different. it's a closed loop instead of a closed surface. Okay, more on that in just a second. That's why you'll hear phrases, instead of a Gaussian surface, we will have an Amperean loop. All right. Equals the current that is inside, whoops, mu naught. The current that is inside of that surface. Well, let me give you a picture, okay? And so as we get ourselves prepared to do some of these calculations, let's look at kind of the author's first Gaussian surface. Let's look at this for a moment. Here is this wire. This is kind of a three-dimension. He's designing it, kind of look like this. Here's the wire, kind of angled back in here. And he's got two little Amperean loops. Let's start with number one. That's all we'll have time here for today. But if I draw a blue line around here on the outside, that's an Amperean loop. Maybe I'll get something more three-dimensional. But if this is the loop, and then this is the current, I would say all that current goes through the Amperean loop, right? Now, if the current was up here, how much current would go through my Amperean loop? Well, none, right? And so, again, just like we did here, we were interested in how much charge was enclosed in this surface. We are going to be interested in how much current is enclosed inside the loop. And so we will be drawing Amperean loops as opposed to Gaussian surface. But either way, we are still looking at a summation. You might call this, say, a line integral instead of a flux or surface integral. But instead of adding up over the whole surface, we are adding up over the line. Okay? And so B is the magnetic field, ds is the little loop. It's got to be a closed loop, just like it has to be a closed surface. This is the current inside, just like it had to be charge inside. This is the permittivity of free space. This is the permeability of free space. Right? And so I hope you can see the analogy. Because I'm hoping we can have just enough time to at least let's do the outside of a long wire. Yeah.
I'm just curious.
Oh, Gaussian. Gauss's, yeah. Magnetism came first, and then that led to, yeah. I mean, I thought electricity came first, and then magnetism. Yeah. Yeah.
So an Amperean loop is actually considered two-dimensional.
Yeah. So you might say a Gaussian makes a surface, so it encloses a three-dimensional volume. An Amperean loop then has a two-dimensional surface that the loop encloses. Again, maybe the best way to do this is by an example, the simplest example. And here's what I mean by the simplest example. Let's do an Amperean loop outside of a wire, radius r. Now here's why I say that. We just got done answering this one. Do you know the magnetic field outside of a very long straight wire? Let's write it down. We already know the answer, right? What was it? B equals what? Mu naught I over 2 pi. Now we wrote it as A. I don't know, do you want to leave it as A? Because I noticed in this diagram he now calls it R. Okay. And so kind of mixes the symbols there. That's just to keep you on your toes, see if you're paying attention. It's the whole idea to make you frustrated, make you drop out, like less scientists and engineers, makes the pay go up for the rest of us. It's a big evil scheme. I told you that before, right? It works well too, right? All right. All right, so switch the whole units there. All right, so let's see if we can do this real quick in a couple of minutes and come up with that answer. And so, let me take that picture and draw an Amperean loop. Well, in this case, the author's already drawn an Amperean loop. So let me look at that big loop, number 1, and we'll stop there and we'll come back on Tuesday and do the inside loop, number 2. And what's the field on the inside? And believe me, this is where, on the inside, just like Gauss's law, was easy to get the electric field on the inside. We were glad we didn't have to do Coulomb's law to get the electric field on the inside. You're going to be glad we don't have to do Biot-Savart law to get the magnetic field on the inside. It's going to be real easy. But that's for Thursday. Let's just do the outside. The outside, we already know the answer. Let's find it by taking this dot product. And so just like we did with Gauss's law, the first thing to do is to take the dot product. And if you know a little bit about the symmetry going on here, we can say a few things about it. For example, what do we know about the magnetic field everywhere on the Amperean loop? It's the same. And here's our argument, just like it was for Gauss's law. I'll stand over here about the same place I did for Gauss's law. If I think of this as a line of current, and I stand back here, the magnetic field that's created here, however big it is based upon the current distribution. If I were to come over at an angle, I would be the same distance away. All the current distribution would look the same. So whatever magnetic field I get here, I would expect here, and I would expect everywhere along a loop. And so one of the first steps to do is to say I can pull out the magnetic field. Whether I know it or not, which I'm assuming I don't know it, although I already did it for Biot-Savart, okay. But assuming I did not know what the magnetic field is, I can say it has the same value along that Amperean loop. And so that's why, just like Gauss's surface, a good choice of the surface made this an easy integral. A good choice of an Amperean loop makes this an easy integral. And so that's my symmetric choice. The other thing I have to do is know something about the angle. Well, that's why we had to do Biot-Savart law a little bit first. What do we already know about the direction of the magnetic field around a wire? It's in the direction of the circle, right? And so if I were to take my right hand and grab the wire with my thumb pulling out, the magnetic field would be in a circle around it, which is actually in the same direction as the ds. So what is the angle here? Isn't that 0 degrees? The direction of the magnetic field and the direction of the ds are exactly the same. They are what you might call in the direction of the circle. They're both around the circle. And so this just becomes a ds. It's 0 all the way around that circle for this case. It's not always 0 for every case. We're going to, again, we're back to your question. We do a lot of the symmetric ones here because we're waiting for your math to build up. And so next semester we will do the off-centered ones. But if that wire was not in the center, it wouldn't be quite so simple. But you could do it once you finish Math 200. All right. So my first part of my integral then becomes b. And then let me just make sure you're following along. What's this?
Circumference.
Yeah, 2 pi r, right? Now let's do the other side of the equation. The other side of the equation, say it should be then the permeability of free space times the current that goes through the Amperean loop. Well, how much current goes through the Amperean loop? Well, all of it in this case. And you can see what's coming up on Thursday that we're going to make a loop that's smaller, so it won't be all of it. But for right now, it's all of it. So I'll just put an I. And so this is just mu naught I. And so B becomes mu naught I over 2 pi r. There it is. And so there's our first calculation. Applying Ampere's law to find what is the magnetic field outside of this long wire. Now if we're in the wire, we have 2 minutes. Should we try it?
Yeah.
I don't think 2 minutes will do a fair justice. So I will stop there. Don't tell anyone you got out of class early. They'll think it's an easy class and everybody will be signing up next semester. And, yeah.
going in through the inside,
Right.
not including the
Just like Gauss's law, exactly.